Have you ever stopped to think about the invisible forces that are quite literally powering our world right now? Well, today we're going to pull back the curtain on the incredible world of electric charge. We're going to start with the absolute basics and build our way up piece by piece to some of the most powerful and honestly beautiful laws in all of physics. It's going to be quite a ride. Let's jump in. All right, so let's get started with a really simple but super important rule. When you have identical conducting things and they touch, they share their total charge. It's that simple. So picture this: three identical metal spheres. Sphere 1 has a positive charge, let's call it plus Q. Sphere 2 has a negative charge, minus Q. And Sphere 3 is totally neutral, no charge at all. Okay, so first we touch the neutral sphere to the positive one. What happens? They add up their charges and split them right down the middle. Now they both have plus Q over 2. Easy enough. Now we take that newly charged sphere and we touch it to the negative one. Same deal. They add up their charges and split the new total. It's all about redistribution, and this basic idea is the foundation for everything that follows. Okay, so we know charges can move around and get shared, but that creates forces, right? We all know the basics: likes repel, opposites attract. But how much? How strong is that push or that pull, really? How do we actually put a number on it? Well, the answer comes from this absolutely beautiful piece of physics called Coulomb's law. This is the formula. This tells you exactly how strong that force is between any two charges. And it makes sense, the bigger the charges, the bigger the force. But here's the really wild part. That little r squared on the bottom. Distance plays a huge role. If you double the distance between two charges, the force doesn't get cut in half. No, it drops by a factor of 4. This inverse square thing is a pattern you see all over nature, from gravity to light. And, super important to remember, force isn't just a number, it's a vector. It has a direction. So Coulomb's law is perfect for two charges. But what happens when you've got, a crowd? Imagine we've got 3 charges sitting at the corners of a triangle. They're all pushing and pulling on each other. Well, no problem. We just focus on one charge, our charge of interest, and use Coulomb's law to figure out the force from each of the others, one at a time. Then, since forces are vectors, we just add them up, tip to tail, like we learned in physics class. The final result is the net force. That's the one overall push or pull that our charge actually feels. This whole idea of adding up forces leads to a really cool question. If we can calculate the total force, could we be clever about it? Could we arrange our charges just right so that on one of them, all the pushes and all the pulls cancel each other out perfectly, so the net force is 0? This perfect state of balance has a name. It's called equilibrium. But here's the thing. Not all balance is created equal. You've got stable equilibrium. The best way to think about this is a marble resting at the bottom of a bowl. You can nudge it, but it's always going to roll right back to the center. Then you've got unstable equilibrium. That's like trying to balance a pencil on its tip. Yeah, you might get it for a split second, but the tiniest disturbance and boom, it's over. And knowing the difference between stable and unstable, well, that's not just theory. It's the difference between building a skyscraper that stands and one that doesn't. So Coulomb's law is amazing for these nice, neat little point charges. But let's be honest, the real world is messy. Charge isn't usually in little points. It's spread out or smeared across entire objects, like a charged metal rod or a plate. So how on earth do you calculate the force from that? Well, the solution is just a brilliant leap of imagination. We basically pretend that our charged object, say a ring, isn't one continuous thing. Instead, we imagine it's an infinite chain of teeny tiny point charges, all sitting right next to each other. And since we know how to handle point charges, we can use Coulomb's law on each tiny little piece and then add them all up. But wait, how do you add up an infinite number of things? Well, for that you need a very powerful tool: calculus. Now, to make that calculus work without our brains exploding, we need a new concept. It's called charge density. Instead of thinking about the total charge, charge density tells us how much charge is packed into a certain length, or an area, or a volume. For a line of charge, we use the Greek letter lambda. For a surface, we use sigma. It's basically a way of describing how crowded the charge is, and it's what lets us tame that idea of infinity. And using this whole integration method, we can figure out the electric fields for all kinds of different shapes. We can find the field from a charged ring, a solid disk, even a massive, infinitely large plane of charge. The formulas we get are incredibly useful, but I'm not gonna lie, the calculus to get there can be a real beast. And that's a classic moment in science, right? You've got this method, this integration thing, and it's powerful, sure, but it can be an absolute mathematical nightmare. And whenever physicists hit a wall like that, they start to think, okay, there has to be a better way. There must be a more elegant path, a shortcut. And guess what? For problems that have a certain kind of symmetry, a special kind of beauty, there is. This shortcut, this elegant idea, starts with a concept called electric flux. Now, it sounds really complicated, but the idea is actually super visual. Imagine electric field lines are like streams of water flowing out from a charge. Electric flux is just our way of measuring how much of that stream pokes through an imaginary window or surface that we draw in space. Think of it like this. If you hold a bucket out in the rain, the flux is basically how much rain is passing through the opening of your bucket. And this simple idea of just counting the field lines leads us to one of the most incredible statements in all of physics, Gauss's law. What it says is, well, it's profound. It says that the total amount of electric flux bursting out of any closed surface, like an imaginary bubble you draw in space, is directly related to the total amount of charge you've trapped inside that bubble. It's this deep, beautiful link between what's happening inside a surface and what you can measure on the outside. So why is this such a big deal? Here's the magic. If your problem has symmetry, if you're dealing with a perfect sphere of charge or a long straight cylinder, Gauss's law is a superpower. It takes that mathematical nightmare of integration we were just talking about and turns it into like 2 lines of simple algebra. It is, without a doubt, one of the most elegant shortcuts in all of science. So let's actually see how this superpower works. We've got these 2 spheres, one inside the other. The process is a simple 4-step recipe you can just repeat. Step 1, pick a region in space you're curious about. Step 2, in that region, draw a nice, symmetrical, imaginary Gaussian surface. In this case, another sphere. Step 3, and this is the key, ask yourself, how much charge have I trapped inside my imaginary sphere? And finally, step 4, you just plug that charge into Gauss's law and solve for the electric field E. That's it. It's that straightforward. And when you do that for each region, you get this beautiful, complete map of the electric field. And look at the results. Inside that inner sphere, the field actually gets stronger the further you move from the center. But then in the spaces between the spheres and outside the whole thing, it drops off with that familiar inverse square law we saw way back with Coulomb. Gauss's law gives us this entire detailed story, and we barely had to break a mathematical sweat to get it. Now, if you're sitting there thinking, okay, that's cool for spheres, but is this just some abstract physics problem? The answer is a huge no. This exact physics is the secret behind the coaxial cable that probably brings internet or cable TV into your house. That structure, a wire running down the center of a metal tube, it's a perfect real-world application of Gauss's law. And here's what Gauss's law tells us about that cable. It shows us exactly where the charges hang out, on the surfaces of the metal conductors. But here's the most important part. It proves that the electric field is perfectly contained in the space between the inner wire and the outer tube. That containment is everything. It's what shields the signal from outside noise and interference, allowing it to travel long distances without getting garbled. It's just a brilliant piece of engineering built entirely on this one elegant law of physics. So let's just take a second and look back at the journey we just took. We started with the simple, intuitive idea of charges just sharing when they touch. Then we gave that a number with Coulomb's law, the force between 2 points. After that, we tackled the messy, real world of continuous objects, using the brute force of calculus and integration. And finally, we discovered Gauss's law, this incredible, elegant shortcut that just tamed all that complexity, as long as we had symmetry on our side. And that leaves us with one last, really big question to chew on. Gauss's law is our superpower, but it only works in a perfect, symmetrical world. So what happens when things get messy? What about the ridiculously complex, asymmetrical world inside a tiny microchip? How do we possibly map out the electric fields in there? Well, that's where modern physics and incredibly powerful computer simulations have to take over. But it really makes you wonder, what's the next elegant shortcut just waiting out there to be discovered?